All right, so let's return to the multiplication rule and let's look at the probability of A given B. So the rule said that this is the probability of B given A and A divided by the probability of B. Once again, I'm assuming that P of B is greater than 0. Now, what we had also from the multiplicative rule is we can apply it to this term up here and get that that term, the numerator, is just equal to P of A times P of B given A. So look what's happened. We have written P of A given B in terms of simple quantities, P of B and P of A. And what conditional do we have here? P of B given A. In other words, the roles of A and B have been switched. So we go from conditioning on B to conditioning on A, which we're going to find very useful when we get to diagnostic testing. Extremely useful. This formula here, or this rule, is called Bayes' theorem. So Bayes' theorem allows us to, let me clean it up, allows us to express the probability of A given B as a function of the probability of B given A, reversing the roles of the conditioning event. It's a wonderful theorem that we'll use repeatedly, especially coming up. Now, sometimes it's not expressed this way. Sometimes we expand. You see that the numerator is expanded. So instead of P of B, we expand it to be P of B and A plus P of B and A complement. And then we write it out like this more fully. But the beauty of it is up here, that we've reversed the roles of what we're conditioning on. And where we use this, we'll use it right away, is in diagnostic tests. So in diagnostic tests, we'll associate the event A with the event D. Let's call it D so we can remember what it stands for. Have the disease. And the event A complement is the event we do not have the disease. And the event B, now what are we going to condition on? The event B is we're going to have as having gone to the test, having had a test done, and the test turns out to be positive. So now we want to know what is the probability of the disease given that the person has tested positive for the disease. Now, it sounds like a silly question. If we've got a perfect test, then this should be 1. This probability should be 1. But what makes this very complicated is that we do not have perfect tests. Our typical biological tests are all imperfect. But let's go back to our Venn diagram. So let's say this upper triangle, so up here are the people with the disease, and down here are the people without the disease. Don't read anything into my drawing the line halfway through. It's just that I have enough space to do all the drawing that's coming up. Then we now have the test positive. So these people test positive. Let's put what those are. Those are the people above the line here. So those are the people who have the disease and test positive. And the people down here are those who do not have the disease and test positive. Now, if we had a perfect test, there would be nobody here without the disease who tests positive. So this would disappear. If we had a perfect test, this would disappear. Also, the people with the disease who don't test positive, that would be all these people out here, that would disappear. So if we had a perfect test, this is what it would look like. Okay? But we don't have a perfect test. So this is what it typically looks like. And we've got people here who test positive who are not diseased. We call these guys false positives. They shouldn't be testing positive. They should be testing negative. And what about these guys out here? They're not testing positive, and they have the disease. So these guys are false negatives. Ideally, we'd love for both of those to disappear. But with the kind of testing, imperfect tests we have, we sometimes have false negatives, unfortunately, and sometimes have false positives. Now, Bayes' theorem gave us this, all right? And you can see that if we've tested positive, we are in this ellipse. So that becomes our universe now, and we can calculate these quantities. So what we've got prior to testing, we have that everybody either has the disease or is disease-free. And you might ask, what about testing positive? What's the probability of testing positive when you have the disease? So I'm making this little 2x2 table for you. That's the 2x2 part. And the answer is, that is what we call the sensitivity. So the sensitivity of a test is how often does it test positive when a person has the disease. How about testing negative? Well, when should it test negative? When a person does not have the disease, it should test negative. That's called the specificity. Ideally, we would love a test where the sensitivity is equal to 1 and the specificity is equal to 1. So for an ideal test or a perfect test or what have you, we have one that's sensitivity and specificity is equal to 1. What about the people who have the disease? We call that the prevalence. And Fran will be talking much more about that. Now, this is before we do the testing. Before we do the testing, we've got this set up. And presumably, the company that manufactures the device that you're using to test will give you the sensitivity, will give you the specificity. From somewhere, local conditions will tell you the prevalence that you're testing with. But those are the three quantities that are going to be important to us prior to testing. After testing, post-testing, or posterior, post-testing, what happened here? Of those who have the disease, how many tested positive? That's this quantity here. Probability of the disease given that you've tested positive. So here we look at everybody who tested positive along that row. How many actually have the disease? That's this quantity here. What proportion have the disease? That's this quantity here. That's called the PPV, the positive predictive value. What about those who test negative? They are these guys. What's the probability of not having the disease given that you've tested negative? That's the negative predictive value. So that's these guys. Okay? And as always, the stuff that's on the main diagonal is the important stuff, and so we've even given it a name. And that's when you can see whether it's important or not. But the point to remember here is that we've got, prior to testing, we've got one set of measures, sensitivity, specificity. Post-testing, we've got another set of measures called the positive predictive value and the negative predictive value. So there is the formula for the positive predictive value. We got it straight out of Bayes' theorem. And if you look and go back to the two previous slides, we see that the positive predictive value is the prevalence times the sensitivity divided by the same thing, prevalence times sensitivity, plus 1 minus the prevalence times 1 minus the specificity. So that's what Bayes' theorem tells us. Bayes' theorem allows us to evaluate what's the value of a positive test. Given that we took this diagnostic test, what's the probability of having the disease? And we can express it. Look at all the quantities on the right-hand side. We can express it with the prevalence. That was known before we took the test on this guy. The probability of testing positive given the disease, that's the sensitivity. We knew that that was established at the factory. And this is 1 minus the specificity. So we knew that before. It allows us to flip this around, the conditioning event, so that we can express it as things we know even before we look at a patient. So we can evaluate this for T positive, we can evaluate it for T negative, and then we can tell the patient, oh, you're going to go and do this test. If it's positive, it's going to mean this. If it's negative, it means that. And we can evaluate all that by knowing these quantities. So that's the value of Bayes' theorem right here with diagnostic tests.